Hey, hi, I'd like to introduce myself. I'm Ben Schmaus. I'm a senior principal software engineer at Red Hat. I'm based right here in Minneapolis. I've been with Red Hat since 2015, although I did take a 4 month sabbatical and worked at Dell for a little bit, but then I came back to Red Hat. Today, we want to talk about demystifying RDMA on Openshift, but I'm kind of curious just from the audience perspective here. First off, how many people are Openshift customers here? Okay. Now, of those OpenShift customers, how many of you are starting to think about doing AI within your business? And I don't mean consuming it like Gemini and stuff like that, actually training models and then also inferencing. Anybody? Okay, great. So you guys will mostly be interested in this then. The rest of you, it'll be very informational, but hopefully it'll pique your interest on future endeavors in your business. So let's go ahead and get started. So, AI is everywhere, right? You turn on the TV, there's commercials about AI. I even tell my wife, I'm like, hey, can AI go ahead and change the tire on the car for me? This slide, it's AI. I generated it with Gemini, and the next few slides are also going to be AI generated. I just want to make that disclaimer, but they're going to get the point across that AI is everywhere in the world right now, and it's the big buzz term. So depending upon where you're at in your business or in your life, AI could be potentially touching you in different ways. So for example, from a consumer perspective, we probably all use ChatGPT in here. We've used Gemini. We've used assistants at company websites that help navigate us, to get an answer on something. But now if we think about the business perspective of it, maybe your business is starting to think about how can I consume AI? How can I use it to help make my business run more effectively and more efficiently? And if you're a developer in here and your business has already made that decision, you're probably involved in using AI to help develop code that's going to run those workloads, that's going to potentially train those models and do the inferencing for you. And I don't know if there's anybody in here, but there is that research arm of it where people are looking at AI and how is it impacting humanity? How is it affecting us as a world going forward? So with all of that, to do AI, you've got to have raw data that you're going to take and input. And then you've got to process that data. And usually you're using GPUs to do that processing. And then finally, you're going to have your outputs in your generated AI data and insights that you'll use for whatever the business challenge is you're trying to accomplish. Our focus here today is really going to be on the GPU clustering processing point of this, because we want to talk about the efficiencies there. And the reason we're going to talk about that is because the GPU cluster processing is not just going to happen on one node. It's going to happen on a huge swath of nodes. You're going to have many GPUs across many worker nodes in OpenShift, hopefully. And that's going to put tax on your networking. You're going to want to make sure you've got some high-speed networking in between those nodes so that you can move those data sets and those model sets in between the nodes very effectively and very efficiently. This is an example of where you can see how data moves for TCP just in general. And what happens is from the GPU, it goes to the PCI switch, to the CPU, to the memory, and then back to the CPU and back to the PCI switch, out the NIC card. The same transaction takes place on the other end. You can kind of see how that's inefficient because you're touching that CPU and that memory. You're going back and forth in that segment 2 times. And I'm just going to finish the flow here so you can see the double arrow locations. That's the inefficiency right there. That's called a bounce buffer. And in order for us to move that data between those nodes, this is going to happen under a regular circumstance. The same thing can be said about moving NFS data from a GPU, large data set. I want to move that out to maybe my NetApp filer or some other storage. Again, you're going to have a bounce buffer in there where you're going to be going through the CPU multiple times to get to memory and then to go back out and then hit that storage array on the outside. This can also happen if you've got NVMe inside the box and you're trying just to write that data to NVMe. So this brings us to what is RDMA? Well, remote direct memory access is really just a way to cut out the CPU from that transaction. It's going to lead to lower latency, higher throughput, reduced CPU utilization. So if you've reduced the CPU utilization, you're going to end up having more CPU for your workloads instead of this data movement. And it's going to reduce the overhead because you're minimizing some of the OS and protocols within the OS itself. So now let's look at that same data flow with RDMA involved. And you'll see it kind of starts out similar, but the difference here is once we hit memory, the memory goes straight back to the PCI switch and then out the network card. And when it comes in on the other side, at the other worker node, it's going from the PCI switch directly to memory before it actually has to go back to the GPU. So there's a little bit of efficiency there, but it could get better. And I'm going to show you the efficiency here as well with the GPU data flow for NFS. And so it's a similar story. We only hit that CPU once, and then we go from memory, we go into the PCI switch, and we go into the network card, and then out to storage. So this brings us to really where there's a big benefit coming from NVIDIA. And a lot of what I talk about today will be NVIDIA focused. Obviously, they're the leader in AI when it comes to GPUs and building giant clusters. And so we're going to be talking about their initiative, which is called GPU Direct RDMA. And so what GPU Direct RDMA does is not only does it cut out the CPU, but it also cuts out the system memory. So I no longer have to move that data to system memory before I move it out the NIC card. And this leads to even lower latency, even higher throughput, further reduced CPU utilization, and further reduced overhead. So what does that look like when you run that data flow? This time, it's basically the GPU directly to the PCI switch, to the network card, and out. Notice we don't even think about the CPU or the system memory in that host. We're directly sending the data set all the way across the wire, and it's going from one GPU to the other on two different worker nodes. Same thing will happen with GPU Direct Storage, which is another take on the RDMA, but it's specifically for storage. In this case, we can write directly to that storage array on the outside. I've actually tested this with NetApp, and so it does work. Another one that I'm working on is Weka file system as well, doing that with a cluster. And there is the other option of doing it with NVMe if you want to write just directly to NVMe. One thing I want to point out with these little workflows is they try to simplify it so we get the concept and understand what's going on here. But one thing I want to make sure people understand is that inside of a node, especially a node with maybe 8 GPUs, you're going to have multiple internal PCI switches. And so if you've got a GPU that's on one PCI switch and you've got a NIC card that's on another one, there's going to be a little bit of latency introduced because you've got to bounce between those PCI switches. The other thing will be, if you're talking about dual socket boxes and you've got NUMA, if you've got a GPU on NUMA 1 and you've got a NIC card on NUMA 2, you're going to lose some of the performance there as well. So the idea would be to pair your GPU with your NIC on the same internal PCIe switch. So that's just a note that I want to make there in regards to that. So what are the considerations for RDMA or GPU Direct RDMA? So if you're going to try to implement this in your environment and you've got systems that have NVIDIA GPUs and you've got the Mellanox cards installed, you really have to think about, one, am I going to do InfiniBand or am I going to be doing RDMA over converged Ethernet or Rocky? And a lot of times what I've seen with customers is if they've already been invested with InfiniBand, they want to reuse the InfiniBand for this purpose. And that's perfectly fine. For customers that are greenfield and don't have InfiniBand, you can use Rocky and you can potentially get the same performance depending upon how you go ahead and set that up and configure it. So either one is okay. Either one is a valid option for configuration. In Openshift, it really comes down to where you're at your business and what kind of technologies you have. The next thing will be high-speed switching. So RDMA will run over any switch. We've tested it on I tested it on a 100 gig port Juniper switch, just general purpose switching. It'll work there, but the performance isn't as good if you were using a 400 or an 800 gig switch. And NVIDIA obviously sells their Spectrum switches, but then you've also got Arista and you've got Cisco and Juniper who are also coming out with 400 gig type switches as well. So the goal here would be is you want to make sure you're using a switch that actually has high bandwidth, high performance. You don't want to do RDMA on a 25 gig and expect it's going to do miracles with data movement. The next thing to consider is your host side components. When you go to install this on Openshift, you're going to have to make sure that you're installing some drivers for the network cards. You have to also install specialized drivers for the GPU. And then there might be in your nodes, you might have this concept from NVIDIA called NVLink. NVLink is a way where you can physically connect all the GPUs together. So if we go back to that scenario where I talked about how we've got a NIC card on one PCI switch and we've got a GPU on the other, what NVLink can do is it can say, hey, this GPU wants to talk to that NIC. It'll go across the NVLink connections and go out the other GPU that's associated with that PCI switch, and you get the benefit of hitting that NIC immediately. And then, of course, your network cards. You got to have Mellanox cards in this scenario if you're going to be doing GPU direct RDMA. Finally, we want to think about validation tools. So a lot of times people will set this stuff up and they'll think, I'm going to go ahead and jump to installing my workloads. Don't do that. You first want to validate that your infrastructure is sound. You want to make sure that this is working properly before you actually run a workload. Because now if I go to run a workload, let's say I run Openshift AI. I've got that installed, I'm running it, but now I'm seeing issues. Are my issues with the way I've configured Openshift AI, or my issues with my infrastructure under the covers? So the goal here would be to validate what the infrastructure is doing under the covers before you go to run your workloads on top. So how do you enable this on Openshift? It's actually pretty easy. There's basically 4 steps here. You install Openshift, you install the node feature discovery operator, you install the NVIDIA network operator, and you also install the NVIDIA GPU operator. We're going to kind of talk about each one of these in detail now. So first with Openshift, however you want to install Openshift usually is going to work here. Your control plane could be bare metal, virtual. You could use hosted control planes for your control plane if you want. But the worker nodes themselves are going to be bare metal because you're needing GPUs and you're needing physical Mellanox cards for your workload. How you do the installation, you can use UPI, IPI, agent-based, assisted installer, whichever flavor you're comfortable with, they'll all work. A lot of the lab work that I do, I use assisted installer to do it. But again, any one of those will work as long as you get an established Openshift cluster. Finally, from a configuration perspective, there's a few things that from my experience have been helpful. One, enabling huge pages. That comes into play, especially when you're doing any of that GPU direct storage pods and you're running those pods and moving data. That's a benefit there. So I just enable them out of the gate. If you have nodes that have an Intel E810 card or any other network card that might load the RDMA kernel module, you're going to want to go ahead and make sure that that is blacklisted with a machine config, because that will hang up the NVIDIA network operators from loading properly. And then finally, if you've got nodes that have a lot of NIC cards, like I worked on one that had 16 Mellanox cards in it, you're going to want to set UDEV rules with the machine config so that there's persistent naming. If you don't, what will end up happening is as you reboot those nodes, sometimes those NICs will come back in different orders and different numbers, and that'll screw your configuration up. So you want to make sure that you're using persistent naming. And even with NVIDIA and their Spectrum X platform, they're also recommending that down the road as well. So it's just a good habit to get into. So the next thing we want to do is install the node feature discovery operator. Basically, you need to have an Openshift cluster to do that. And really what this operator is doing for you is just labeling the nodes to identify, yep, you've got GPUs in here. Yes, you've got NIC cards in here. These NIC cards might have SROV enabled, but it's making sure that the nodes get labeled properly for the right feature and functionality that's in those boxes. And the one thing I'll point out is, while the default instances and stuff for the NFD operator should work for you, I like to actually configure my device whitelist class and always add these numbers, which are specific for the NVIDIA GPUs and the Mellanox cards. Again, personal preference, but it's been a good practice and it hasn't steered me wrong in any of the situations I've been in. I added this one in here because it might come into play depending upon what you want to do. So you may want to have SROV in the environment. You may want to go ahead and take those NICs and split them out into virtual instances so you have multiple interfaces. Again, this is really going to depend upon what kind of workloads you're doing and what kind of work you're trying to accomplish. The key thing here that we want to pay attention to once you've installed the operator is that you want to make sure you patch the operator to work with the NVIDIA network operator. So it's basically, what I mean by patching is that it's aware. You want to make sure that the SROV operator is aware you're going to be using the NVIDIA network operator. So there's a patch command. It's in the official documentation on the Openshift site. So that command exists, but you want to make sure you do that. And then finally, there'll be additional configuration steps you'll want to take once you've installed the network operator. And those include, defining your SROV network node policy and your SROV IB network if you're doing InfiniBand, and SROV network if you're doing Rocky. So the NVIDIA network operator is one of the primary components required for this whole setup. And the reason being is because GPU direct RDMA or GPU direct storage can't happen unless you use this operator. And the reason being is that even though we ship the Mellanox drivers with Red Hat Core OS by default and Openshift, those drivers do not contain the special magic for the GPU direct RDMA and the GPU direct storage. That comes with this operator. What this operator will do when you define a NIC cluster policy is it will go ahead and it will unload the in-tree drivers. It will compile out-of-tree drivers that contain that special logic for the RDMA, GPU direct RDMA, and then it will load those drivers in place. And that will give you the capability. What this means is that you'll see a slight blip in that process when it happens on your networking, and then everything will be running just as normal. For the configuration, you can use the default configuration in most cases. Usually I'm defining a driver version because we're trying different versions of the driver. Sometimes we're trying older versions of the driver just for the testing that we do. There'll be other things like NIC configuration operator, which allows you to actually configure the NIC card. So if any of you have used Mellanox cards, you know that they've got a lot of different ways of configuring them as far as you could turn on, SROV within them. You can configure whether they're in DPU or NIC mode. You can configure whether they're in InfiniBand mode or an Ethernet mode. The configurator operator is NVIDIA's way of approaching that from a Kubernetes-centric perspective. You can feed it a custom resource file that will define the things you want to change, and it will make those changes for you. And then finally, there's this SpectrumX operator, which is part of NVIDIA's complete software stack for networking. So what NVIDIA sees happening is they have their SpectrumX switches for the physical hardware, and then on the nodes, we have the cards, and then we have software that's run on those cards that NVIDIA specifically provides. And it creates this software stack that's supposed to be very efficient in moving data and stuff for all these workloads. The SpectrumX piece we're still working on with them to get out in Openshift. So that's a future thing that's coming. And then finally, this usage type. So when you use the NVIDIA network operator, there's really 3 different use cases you can use here. There's this one called RDMA shared, which in simplest terms, it's to say one NIC shared amongst many pods. In your NIC cluster policy, you can define and you can say, hey, I want this NIC to use, or this NIC to be shared among X number of pods. The default is 63, but you could change that to 8, whatever you want to do. But what that means is that all of those pods would be using that one particular port and sharing amongst it. That may not be something you'd want for all your workloads. That's where legacy SROV comes in. In this case, you can create VFs on your NIC, and then you can have more segmented environments if you so choose to do so with the legacy SROV. And then finally, there's host device. I haven't seen anybody actually using this particular one, and I think partly it's limiting. If you only have a couple of NICs in the box and you pass one up to a pod, you can really only use it for that pod. There's no way to use it with anything else until that pod goes away and a new one starts. So I could see using that maybe in environments where you know the entire node is just going to run one giant workload, and that's all that's going to run on it. The other thing about the NVIDIA network operator is there is this concept of environment variables. And one of the things that they haven't done is on these first 3 line items here where it says unload storage modules, restore drivers on termination, and create if name udevs, is these seem to be required when I go to deploy this in Openshift, but yet they're not part of the default policy that is there. So I always add these in. So these are ones I would just say, stick them in there. Otherwise, it's going to complain when you go to create that policy. The last 2 are really specific to, one is to GPU direct storage. And so you're going to have to use that enable NFS RDMA if you want to use GPU direct storage with a NetApp filer, for example. So this one, you don't need to put it in there if you're not interested in doing that. But if you do need it, it has to be in there and it has to be set to true. And then finally, the entry point debug. I just run this all the time as true because 9 times out of 10, if something doesn't work quite right, you're going to want the debug logs. So you're going to have to go back and reproduce the failure. If you've already got this set to true, you could just grab the logs, get them to support, and we'll be able to see the failure right away. This does not create a lot of logs for you because the only thing that's happening when this particular pod drives or runs is it's going ahead and it's showing you the build process, the removal of the in-tree drivers, and then the addition of the out-of-tree drivers. So once that's all done, it just goes to sleep. So you're not going to get logs and logs, reams of generated logs. So it's safe to put that in there without any concern. And that finally brings us to the GPU operator, which is the last piece of the puzzle here. So again, you got to make sure you've got Openshift installed, the NFD operator, the network operator, SIROV if you are using it. And here you're going to install the operator, create a GPU cluster policy. Again, these are some of the things that I found are kind of important to know about in that policy. The default will always set the kernel module type to auto. While that should work, I'm particular about how I set things up. I will always change it and set it to open. And that's basically just means it's using the open kernel module driver. The next one is GDR copy. Set that to true. This is going to allow the CPU to directly map and access GPU memory. That's going to help with efficiencies as well. RDMA here could be set to true or false. Originally, it used to be true, and that was because NVIDIA wanted you to use their NVIDIA PureMem module. But they've changed their positioning on that, and I think maybe what they're trying to do is get away from the NVIDIA PureMem module. You can use DMA buff, which is built into the kernel. And so that's why it could be true or false. If it's true, you're going to use the PureMem module. If it's false, you're going to use DMA buff. Either setting will work. Either way will get you the same benefit. And then finally, GDS, which is GPU Direct Storage. You're going to want to also enable this to true here. The one thing I'll point out is with the GPU operator, when you enable this to true, you have to actually manually set the image location and the version for this. And a lot of times I'm going out to the GDS GitHub page for NVIDIA and just finding the release there. So this is something that they could improve upon as far as if I'm going to go ahead and set this to true, it should already have the values populated for a customer. So that brings us to, assuming we've gotten everything installed, the whole validation perspective. What I call validation tooling. And so what we did is we came up with this thing called the NVIDIA tools image. So what I was finding is a lot of customers would come to us and they would say, things aren't working, and I ran this image. And I'm like, well, where'd you get this image? Oh, I found this image on the internet somewhere. That image wasn't necessarily designed for what they're trying to validate and do. And so we came up with a collection of tools that we were finding we were using a lot of, and we threw them onto an image here that is now publicly available with the Quay image listed down here at the bottom. It's also referenced in the Openshift documentation for RDMA, so it's listed there as well. And then I put the GitHub repo there too, which is my own, because I'm the one that actually put this thing together. The GitHub repo is going to show you how the image is built, what's kind of packed in there, how to run it, and then some examples of what you can do with the image. But the reason I thought it was important to show the GitHub repo is because a lot of times customers, they want to leverage this stuff, but they'd also like to pack in their own personal tooling. And so you could do that. You could say, I'm going to go ahead and build my own image. I'm going to do everything you're doing here, but I'm going to also add in maybe some, proprietary stuff from my business that's going to help do some validation for me. But here in this validation tooling image, we've got things like the Mellanox firmware tools, iPerf, ShowGids, perf test tools, the NVIDIA CUDA toolkit, and the NVIDIA collective communications library. We're going to talk a little bit about each one of those just to kind of show you what that's all about. First, the Mellanox firmware tools. So remember when I talked about the NIC configurator operator? If you're not using that yet and you're familiar with the MFT tooling, these are the tools that are going to allow you to make changes to a Mellanox card. I can change the card's mode. So what I mean by mode is if it's a BF3 card, is it in DPU mode or is it in NIC mode? Sometimes they ship in DPU mode and you want it in NIC mode. This tooling will help you make that change on the card. Is it running in InfiniBand mode or is it running in Ethernet mode? You can also make the change here. So for our testing, for example, we can go ahead and we can change the card from running in InfiniBand mode to running in Ethernet mode. Of course, we have to change the physical connection and make sure it's attached to an Ethernet switch instead of an InfiniBand switch, but you get the idea. You can make changes. You can enable, disable SIROV. You can define how many VFs are going to be supported for SIROV using these tools. You can even do cable checks and power for the fiber optics by running some commands that come with these tools. And then this screenshot here is really just an example of one of the things you can do with the tooling using MLX config. The -D is a device name, so that's the PCI device address. And I do a query, and then I pipe it into a grep. And I wanted to condense this because if you just ran the query, you would get a really long page of configuration items. I just wanted to show you that you can get some things if you want to narrow it down, but I didn't want to display the entire page of configuration items. So here we're just looking at the number of VFs, which is the number of virtual functions supported on the card. In this case, we've set it to 16. And then SROV is enabled. And in this case, the link type is set to InfiniBand. So this card would be used in SROV scenario for InfiniBand if we so chose to do so. If you change that query to a set and then add, num of VFs equals and put in a different value, you could set the number of VFs to a different value in that example. So I included this, although this really does not help us with RDMA testing, but I kind of wanted to use it as a sanity test. iPerf, obviously, a lot of people have used it for networking. They're familiar with it. What we've included in here is a couple of scripts that came from NVIDIA. Those scripts basically set up a server side and a client side. So what you end up doing is if you've got 2 worker nodes, you're going to run a pod on one worker node and a pod on the other one. One will become your server and one will become your client. On the server side, you'll say, how many cores do I want to use? In this example, I'm using 12 to 24. It's going to fork an iPerf process onto each one of those cores. And then you go over to the client side and you say, I want to hit the other pod, which is going across my Mac VLAN network, hitting the IP address of 192.168.10.2 in this example. I'm also going to use 12 through 24 cores, and I'm going to run it for 30 seconds. And when you run that, it'll spill out a bunch of information. I just went ahead and grabbed the last number because that's really what's important to me. And you can see we got 289 gigs per second across this particular link. And this is on a host that's not even on a group of hosts that's not even really what I would call optimal hosts for doing this kind of test, but that's what we got. And this is across a high-speed Spectrum X switch, SN5600. So then I included this little script called show GIDS. And this one's important because this is going to provide you with some information you're going to need when you run the perf test tools and when you run the NCCL tools. And so the key things to point out here is when you run show GIDS, it's going to give you a device, that MLX5 underscore some number. It's going to give you some index numbers. You're going to see the IP address over there in the IPv4 column. Most of the time that IP address is associated with the interface that you have with the pod that you're on. And then there's the version number, which is the version of Rocky. Are we doing version 1 or version 2? So the key here is you want those values. You're going to use those values in the next thing. So this isn't really doing anything with RDMA. It's really about gathering information that you will need to run those tests in the next few slides that we look at. The CUDA toolkit is basically the GPU accelerated libraries, debugging and optimization tools. There's a compiler, runtime libraries. This doesn't really help you validate RDMA, but this is needed in order to compile the perf test tools and in order to compile the NCCL tools, which is the things that we actually will do on the fly when you run this image. So it's included here because it's a requirement, but it's a requirement for you only because you need it for those tools. It's not a RDMA test type tool. And so that brings us to the perf test tools. This is probably the one that we use most of the time to do our perf testing when we're validating the network, the NVIDIA network operator and its drivers. This is a collection of bandwidth and latency benchmarks. You can do IB write latency, IB write bandwidth, read latency, and read bandwidth. We tend to focus on the IB write BW. If we're getting good numbers there, we believe we're going to get good numbers on the rest of them. So most of our testing focuses on IB write BW. You can see in this example, I tried to squeeze in, so we have a pod on worker 1, for example, and we're going to run this IB write command. And you'll notice the -X there, it's got a 3. That 3 is the index number that we would have got from that show GIDS command previously. The other thing that's important here is the -D. Notice it says MLX5 underscore 1. That would have come from your show GIDS output that we saw in the previous slide. And then finally, we're going to define a source IP. That source IP address is actually the IP address if I do an IPA on this pod in this worker, and that's going to be the interface that's been passed up from Openshift to this pod. And then finally, one other thing I'll point out is there's that use CUDA. If you have multiple GPUs associated to this pod, that use CUDA could be 0 because it might be the only GPU, but if you've got more than one, you might say use CUDA equals 1, 2, 3, however many GPUs that you have associated with this particular pod workload. And then finally, because I'm not using the PeerMem module here, I added on the use CUDA DMA buff. That ensures that we're using the DMA buff test with this particular run. And that's just for the server side setup. Then we go to worker 2, and there's a pod running over there, and we kind of run the same command. Notice our -x is different because the index number is different on that particular node. So you're always going to have to run show gids to show you the values. Our -d is still MLX5_1. We just got lucky there. Notice our source IP is going to be the IP of this pod, but now we've introduced the destination IP address of 192.168.10.2 because that's the worker 1 pod that we're going to be hitting to complete our test. When you run this test, both screens will show you the same information, and then you'll eventually get this output at the end. And the BEW average is really the number that we're shooting for. This particular lab has got 2 R760 XAs. They don't have the NIC GPU set up to be very efficient. They're on different NUMAs. They're also on different PCI switches. So our number is only 178 here on a 400 gig link. I've worked with some partners like Cisco and Dell where they've actually had 8 GPU boxes and they've had 8 NICs on those boxes and the alignments are appropriate. You can almost get line speed. It's about 389 gigs per second when you run this test. So you're moving a tremendous amount of data if this is optimally configured for you. My test, not so much. And that finally brings us to this NVIDIA Collective Communications Library. It's pronounced nickel, you might hear it. This is another way to do testing. I will say I am not an expert with this one. I find it very complicated, but I did manage to come up with a scenario that allowed me to test the same 2-pod workload scenario like we just did with the IB write BW command. What this involves is you're using MPI run and you're specifying the 2 different pod IP addresses. And then this image tooling that I built actually has SSH servers running on each side so they can communicate over SSH. And that's what ends up happening is the MPI run will connect via SSH to each of these nodes, and it'll go ahead and it will run the rest of this command. I don't have all these switches memorized. I'm going to be honest. I have to always look up what these switches mean. That's what man pages are for. So I couldn't really tell you. I can tell you this. I believe the B was 8 GPU here. So that is the one that I do know. And then, of course, this is a memory. But the rest of these I usually have to reference and figure out what I'm doing if I want to try to change that test around. And this is the preferred NVIDIA testing. So they like to see these numbers versus the IB write command. But again, you'll have to figure out what's going to work best in your environment. So after all of that, if we feel comfortable that everything is set up and we're getting the right values in the numbers, everything that we covered was really in that dotted blue box on the bottom. But what that ensures for us is that we've set our infrastructure up right. And so at that point, you are now ready to go on to do Openshift AI or Slurm or whatever the thing is that you want to land on top of Openshift because you know that everything's been configured properly and effectively. So then if you run into an issue with Openshift AI up top, you know it's most likely not my infrastructure. I must have misconfigured something in Openshift AI. And that's all I had for you today. I guess one more thing. Any questions? Sorry. No? You all just want to eat, right? All right, thank you.